In this video, I'd like to touch on a few concepts used in reservoir simulation. The content of this video is largely drawn from Chapter 19 of Petroleum Reservoir Engineering Practice by Enemeka Ezekwe, and of course, other sources. In the past, we've looked at what reservoir simulation is all about, but just to recap, reservoir simulation is more succinctly defined as the means by which a numerical model of the geologic, petrophysical characteristics of a hydrocarbon reservoir is used to analyze and predict fluid behavior in the reservoir over time. And to do this, a number of disciplines, skill sets from different disciplines are brought together, all for the purpose of predicting hydrocarbon performance under different operating strategies. And this helps the company, the producing company, to gain an understanding of the dynamic behavior of the reservoir, quantify uncertainty, compare scenarios, and it aids in locating wells, and also optimizing surface and downhole facilities. So a model of the reservoir is built and executed such that it tends to replicate the behavior of the reservoir, it mirrors it, and that's why we use the term simulation. It mirrors the observed behavior dependent on the data available and the maturity of the reservoir system. So the numerical model consists of several of a sets of mathematical equations and still built on the concepts you are familiar with: conservation of mass, a transport equation, Darcy's law, for Sherman's equation in some instances, and other physical processes, of course, subject to constraints and boundary conditions. So different forms of this mathematical model could be developed or represented, as the case may be, depending on the nature of the reservoir and the physical systems we are trying to simulate, and of course, subject to the objectives. So in this presentation, I will be biased towards black oil models, but of course, some mention of compositional systems will be made. So this figure 1 here gives an overview of major steps involved in a reservoir simulation study, starting with setting the study objectives down to setting out production and injection schedules. And if we go through it, even though this is not comprehensive, after your study objectives have been set, you need to compile your input data, of course, from different sources. And most of the time, you will need to import a model, a geological model, into the reservoir simulation environment. And then you now determine the simulator type, which is more suitable to your data, whether you're going to be using a traditional black oil model, a thermal system, chemical compositional, and then at this level, you're beginning to consider grading, and this But first of all, before you talk about the grid system, we're talking about the size. Is it a regional model? Is it sectional? Is it a single well model? And then in capturing the flow between the different units, both across and along the system, would it be appropriate to use a radial grid, Cartesian grid, corner point grid? And then when all that is decided on, you need to initialize the model. And of course, that's after you've specified or imported your fluid and rock properties. And then at the initialization, you set conditions at your contacts, initial pressure conditions, and then specify the solution scheme, and then how you go ahead to manage well data. And these are some of the things which I've highlighted in the one major step that is missing from figure 1 is the history match of the simulation data to actual data. Since after the reservoir simulator is constructed or selected, as the case may be, the model must be tuned or history matched to available reservoir and production data, since much of the data in the typical simulator needs to be verified. And it's the history matched model that is basically used in making predictions. This is a more robust schematic. And then here you see geological and geophysical modeling has taken place, reservoir characterization, you see the different sources, data sources, and then a geological framework is built. And here it's upscaled. I think I have a slide on upscaling, which kind of gives a good illustration of what upscaling is all about. And then you now have your fluid flow model, depending on the availability or the stage of development. If you have production pressure and production data, is history matched, and then the history matched model can now be used in predicting production profiles under different scenarios. So the next thing is into how reservoir simulators are categorized or classified. So reservoir simulators can be classified using different approaches. The most common approaches are based on the types of fluid being studied and the recovery processes being modeled. And okay, other approaches are to look at dimensionality. Is it a 1D model, a 2D model, or 3D model? Number of phases, the coordinate systems you want to use. So the type of reservoir simulators can also be determined by rock structure or response. Is it a typical single porosity system, a dual porosity permeability model, or one coupled with hydraulic and thermal fracturing? So these are considerations that need to be made. So if to classify reservoir simulators based on the type of the reservoir fluids, you look at black hole simulators. Black hole simulators are conventional reservoir simulators, and they are used in cases. So black hole simulators are used where for recovery processes that are not sensitive to compositional changes in the reservoir fluids. And of course, the fluids are treated as separate immiscible phases, oil, water, gas. So black hole simulators are used when the reservoir fluid is typically dry gas, black oil, and then if you want to simulate immiscible recovery processes. And this gives you an idea of the fluid systems for which you would use or select the black hole simulators. In contrast, compositional simulators are used when recovery processes are sensitive to compositional changes, and these include primary depletion of volatile oil and condensate reservoirs. Miscible flooding operations, whether it's first contact miscibility, multiple contact miscibility, and for these systems, you representing the reservoir fluid by just the bulk, oil, and gas phases will be insufficient. You need to represent the reservoir fluids in terms of hydrocarbon components and water is treated as a phase. So as regards recovery processes, you could have, so you have black hole simulators. As mentioned, black hole simulators can handle immiscible recovery processes. However, for miscible displacement, you will need different type of simulators, also for thermal recovery and chemical flooding processes. So for primary oil recovery processes, such as water drive, solution gas drive, gas cap expansion, gravity drainage, capillary inhibition, these all can be modeled with the black hole simulators. And also for secondary recovery processes which involve immiscible displacement, they can also be modeled using or simulated using black hole simulators. For thermal recovery mechanisms, which involve steam floods, in situ combustion, an equation of energy conservation will need to be added, and therefore you will need thermal simulators. Thermal simulators are used for simulating these processes. If you want to capture chemical enhanced flood recovery, you will need to use a chemical flood simulator. These are applicable for processes, alkaline surfactant polymer flooding, foam flooding, basically for systems where you change the mobility ratio dynamically, or you need to use a residual you need to use a surfactant to mobilize residual oil. And there are additional effects that you might need to consider, cases where you have permeability reductions or waterability changes. You need to consider non-Newtonian fluid systems. Other simulator classifications, there are streamline simulators. These are widely used for upscaling large geological models and also for capturing fluid flow between injector producer pairs, which especially when you want to look at saturation profiles. Streamline simulators really come in handy. And for streamline simulation, rather than the grid techniques, which I'll be discussing later, basically you're just looking at flow profiles. For dual porosity simulators that have been mentioned before, these are relevant for naturally fractured reservoirs, which exhibit dual porosity behavior. So let's look at numerical methods for solving differential equation problems. And there are typically three major methods. You have the finite difference method, the finite volume method, and the finite element method. And you need these numerical methods because the differential equations, the partial differential equations, which are formulated in the course or which you are trying to solve, need to be discretized. They're not considered as continuous systems, so they need to be discretized, and these numerical methods help you with that. So both the final volume method and the final element method are integral schemes. And in terms of approximation error, The integral schemes tend to be superior to the finite difference method. However, the differential schemes are generally faster, and the error can be minimized if, of course, if you're using regular grid systems. Well, I'll talk about that in a bit. And even though the integral schemes are slightly slower, they are preferred whenever your mesh system is irregular. So the the finite difference method is preferred for systems where you have regular grids, while for irregular grids, the integral schemes tend to be preferred. So the finite difference method is a differential scheme, and it's based on the approximation of the Taylor series expansion. The first order and second order differentials can be written in terms of the difference between 2 points. In this video, I'll be showing you the first order differential, and then you can look up the second order differential. So as discussed in well testing, equations that govern fluid flow in porous media are partial differential equations, and equation 1 gives the diffusivity equation governing one single phase flow in one dimension for a slightly compressible fluid such as oil. I know you are all familiar with this, even though I think what we did in the well test class is radial flow. And so the spatial and temporal variables, spatial variables, of course, referring to dimensions, temporal or for time, can be denoted as shown, of course, for spatial x in these terms, u refers to superficial Darcy velocity, and this is a differential volume showing flow in the x coordinate direction. So we'll go ahead to look at how you can use the Taylor series expansion to develop the numerical model. So if you consider a function, even though it's P, you can still look at it in terms of pressure, but not necessarily pressure. If you look at the function, so in this, we're treating, in this material, we're looking at the first difference quotients for functions of two space variables, that's x1 and x2, and that of time. It can be downscaled to one space variable and also extended to 3 space variables. So if you consider a function p in terms of x1, x2, and time, the partial derivative of p with respect to x1 can be defined using any of these 3 equations. If you look at them critically, so here, the increment h1 is added to x1. In this time, the increment h1 is subtracted. And in this one, the h1 is both added and subtracted. And you will see this more clearly. So the Taylor series expansion for the function is as shown here. And you see, of course, this has been truncated to the third term. You still have the full expansion still continues. So if you taking this equation, you could write the first order differential. You could write this in terms of the second term on the right-hand side. Just take these, the first term and the third term to the left-hand side, and then you'll be able to write this in terms of this. And if you do that, you would have equation 2 here. So this first term on the right-hand side, this expression is referred to as the forward difference quotient, and that approximates the differential. Of course, clearly you see that this is just an approximation because you have several other terms which are not captured using this. And this brings it clearly that using this, whether the forward difference quotient would introduce an error in the order of H1. Similarly, if you could also have used them. You could also come up with the backward difference quotient, and this also will give you an error in the first order of H1. Now here I've included this slide to illustrate the difference between the forward difference quotient, the backward difference quotient, and then the central difference quotient. And if you look at this, so you see this is x plus h, this is x minus h, and this x minus h, x plus h. And this is just to illustrate those quotients. For this particular slide, the Taylor expansion for these two functions have been given. And if you subtract them, it would now give you this. And from here, you can get the central difference quotient, which approximates the differential, the P, the X1. For this one, you'll be having your error function in the order of this. So it's sometimes necessary to use the difference quotient to approximate the differential computed halfway between x1 and x1 plus h1, and that is what is illustrated here. But the quotients are similar. In summary, we have defined three different force difference quotients in x1. The same quotients can be introduced for x2 and x3, and the second order derivatives can be obtained involving the fourth order derivative of P1 from the Taylor series. Now let me talk a little bit about grid systems. And so if you look at the progression, you have partial differential equations. They are discretized using numerical techniques. Here we're using the finite difference method. And of course, we've seen the three different quotients. So we now talk about the grid systems. And so the discretization in space of the different forms of the flow equations in reservoir simulation requires the use of grids. So the aim of gridding is to turn the geological model of the field into a discrete system on which fluid flow equations can be solved. So the grid structure is the geometry of the computational grid, which can be Cartesian, radial, or distorted. You see that in the first two slides. So there are some key factors that influence the design of the grid system for reservoir simulation. One is the resolution of the geologic and petrophysical data, the size of the static geological model, limitations of the size of the flow model, potential uses of the reservoir model, and upscaling. And even though I won't go into all this in detail, but first of all, your grid system needs to be able to capture the required detail in your reservoir characterization exercise. Say, for instance, in designing the area grid system, if the grid dimensions are too large, your geological features will be poorly represented. Similarly, if you have log data available at about half-foot interval, your grid system has to be at that resolution so that you capture the data. As regards size of the, or size or limitations on the size of your static model will determine the number of grid blocks that you would want to use. Size, and then also the computer resources available to solve the flow equations, because the larger the grid system, the more equations you need to solve and the more computing power that would be required. And of course, if you want to capture flow across a fault, for instance, you need a lot of detail around that system. And that's why I say the potential uses of the reservoir model can directly influence the design of its grid system. For instance, a reservoir model designed to evaluate the impact of fluid properties on hydrocarbon recovery may require a finer grid system than that which is used to investigate the effects of faults on reservoir performance. Since reservoir models are based on geological models, the potential uses of the reservoir models should be considered in doing this. But take note that even though it said that you might need a final grid system, it depends on, of course, the faults are usually far out from the wells, and probably you may just be looking at transmissibility of the faults, but depending on your study objectives, that will determine the grid system which would be used to capture flow at the well and flow at a place like the fault. Now, upscaling is another consideration that you need to put in mind, and that's why I've included this. So, if you look at this, look at the schematic here, you have, these are three different models of the same system. So you see, it's like an injector producer, pair, yes, injector producer pair, of course, with decreasing cells, number of cells as you go down. So the CPU, and with the increasing number of cells, that increases the CPU time involved in running your simulation. Of course, with very powerful PCs, this is becoming less of a concern. However, if you are looking at a full field simulation, you will need to consider this. So an accurately upscaled, so this is like the fine geological model, and this is upscaled, and this is further upscaled. So an accurately upscaled simulation model has got one. If you look at the, so one of the important things is at the breakthrough times, that's the breakthrough of your flood front at the producing well, are they similar? Is it similar in the upscaled model to the fine grid model? Also, the shape of the flood front, if you look at this, you see that two things are quite identical across the models. You see here, there's a breakthrough. Here, look at this saturation profile here, and that's captured in these three models. This particular streak is not quite captured here, but you see that the general profile of the displacement front is captured. And then another thing is the recovery captured from the models, is this similar? And if it's a yes for this, then you have a well upscaled model. So in upscaling, what they are basically doing is you're reducing the number of simulation grid blocks in such a way that the general geological framework is still honored, but then you have less CPU time to run it will require less CPU time for you to run your models. So let's go on to more about grid systems. So the most common type of grid systems in reservoir simulation are the Cartesian those based on Cartesian coordinates. And then they could either be block-centered grids or point-distributed grid systems. The block-centered grid system is what you have in figure 4a, while the point-distributed grid is what you have in 4b. Let's look at these two grid systems in a while, briefly. So for the block-centered systems, you see that the grid block is defined by a central point. So this is U0, U1, U2, U3, spatially distributed equally. Now, for the point distributed grid, it's a little different. So the grid is actually defined by the vertices. So you see U0 and U4 are at the boundaries of your grid system. So based on that, the other grid points are now defined. And that's why if you look at this, so for both grid systems, the grid cell length is actually pretty the same, but the number of grids, this one looks like a half grid. So this is 1, 2, these are three grids, 3 grid cells, and this looks like half grid cells, or like this one where you're having 5 grid cells. So the block center grid is better for calculating mass accumulation, while the point distributed grid is more accurate for calculating flow between grid blocks. So for flow between grid blocks, the point distributed grid is preferred. For capturing mass accumulation within the grid blocks, the grid centered system is preferred. The differences between the two grid systems are quite insignificant, provided the Cartesian grid is uniform. And even though most simulators use block center, but I think many modern simulators now make provisions for different grid system types. So the Cartesian grid system can be classified as 1-dimensional, 2-dimensional, and 3-dimensional. So let's look at the utility of these different grid models. So for the 1D model, it allows you to simulate flow in a single direction. And of course, it has limited applications, but you can use this grid model system to study fluid flow in core displacements in laboratory or slim tube displacements in the laboratory. So if your reservoir system can be described using a core system, for instance, you can't use a 1D model for it. You can also use 1D grid models to study gravity drainage, even though that is to be severely limited. And so basically, if you're just looking at fluid flow in one direction across blocks, and you can see here this with some nomenclatures from 1 to n, and then you have one of the blocks being I, and this is I minus 1, I plus 1. So basically, these grid systems are used for core and slim tube displacements, especially for simulating laboratory processes. For the two-dimensional grid models, these are historically the most widely used models, and they are employed for, especially when you have a single well system where you need to look at cross flow or area flooding problems. So this is the area grid for the 2D area grid. So this is like an XY system, as you can see this. If you want to look at area flooding, of course, maybe you have the injector here and the producer here. The 2D area grid will be suitable for that use. Now, if you are looking at vertical stratification, for instance, you need to see how, for instance, let's say you're having multiple completion layers, and you just want to probably just look at the effect of stratification, or you are looking at a system where you are having you really want to look at a gravity drainage reservoir. You could use a simple cross-sectional. So this cross-sectional model is like an a YZ or XZ model. Of course, 3D grid models are, with the advent of powerful computers, these are the most preferred. They allow for assessing flow or evaluating flow in all directions or in the three directions, and they use for most studies. Of course, this requires much more computational time, particularly if you are looking at a multi-phase, multi-component flow system. But nowadays, 3D grid models are the norm used, except if you are looking at screening studies or you want to simulate simple laboratory studies. So your grid system can also be based on radial coordinates, r, theta, z, and the radial grid systems are used mainly for representing wells in which you have rapid changes in fluid saturation in the near wellbore region. For instance, if you want to look at gas cupping, gas cupping, you want to look at water cooling, and these are systems where you are having gas rapidly entering your wellbore, or you're having water from beneath entering your completions. The radial grid system would be appropriate for that. In some applications, you might even use a hybrid grid model. So if you look at figure 7, you see you have a radial grid, and the circle in the middle here represents a well. So this is like a radial grid embedded in a Cartesian grid system. Apart from the Cartesian grid and the radial grid model, you could also use a corner point geometry, and this requires specifying the locations at the 8 corners of the grid. So you see, this is based on the regular cube system, and then the coordinates at each point will be specified. This gridding system is useful for representing complex geological geometry such as faults, permeability barriers, irregular boundaries, and sand channels. One challenge with this system, though, is that for some highly irregular grids, it may tend not to be orthogonal, and for non-orthogonal grids, it could yield some errors in your flow simulation results. However, in many simulators, they have a number of correction factors which are used. I've also included this to show that the grid, the corner point geometry is not limited to, because it's a Cartesian system. So if you look at this, even though this is Cartesian, this is a different polygon system, and all that is required is at the vertices, the coordinates should be specified. Now, for unstructured grids, you have the Voronoi grid. This is more like the perpendicular bisection grid type. And the Voronoi grid block is defined as the region of space that is closer to the grid point than any other grid point. So this kind of leverages on ensuring local orthogonality. That is, even though the grid system is not orthogonal, it's ensured that between the different grid plus systems, orthogonality is maintained, and so the errors are minimized, and it's flexible for representing complex well geometries, such as horizontal wells and even different features such as faults. If you look at it, these are different Voronoi grids. You see, this is a Cartesian system with the grid blocks having different dimensions. This we'll still talk about this briefly. Locally refined Cartesian grid. This is cylindrical. So this looks like a modified radial grid. This is hexagonal. This is curvilinear. This is a hybrid Cartesian with hexagonal, and then this is hybrid hexagonal. So if you look at and this figure 10 just highlights the flexibility of the Voronoi or the PEBI grids. If you look at it, you see this is horizontal well in what looks like a Cartesian grid embedded in hexagonal grids, and here you also have some horizontal grids and some hybrid grids rather. So this just goes to, of course, if you are developing a simulator yourself, you have more challenges coming up with the flow equations for this system. But these grid systems they are systems which you could select for, you could specify within the reservoir simulator, within the reservoir simulator, whether it's commercial or open source. So you could specify the type of grid system you'll be using. And of course, you could even do a sensitivity study on different grid systems to see the ones for which capture flow, depending on your fluid objective, your study objectives, and have the minimal errors. So I've included this slide to show you that the gridding is not just blocks or shapes. What you're trying to do is to capture. So for most studies, what you'll be doing is importing a geological model, and then within the simulator environment or within the integrated modeling environment, you now be coming with simulator grids. Remember that your simulation grids is to enable you solve the flow equations between across the model. And you see here it's mentioned that important, so your grid system should allow for the capturing of important geological features, should maintain orthogonality and smoothness, and then, of course, you should be able to capture gravity drainage, of course, if that is an objective of your study. So what is the concept of local grid refinement about? So it's a technique used to increase the grid density in regions of the reservoir where rapid changes in saturation and pressure are occurring. And as you've seen it in some of the previous slides, you see that local grid refinement tends to be used around in your near wellbore region. At times, you could also use it around your contacts. So local grid refinement is used mainly around well locations or to monitor saturation changes at fluid boundaries. An example of local grid refinement is shown in figure 11. So this is the regular grid size, and then here is further refined. So within one grid size, you're having a 5x2 grid. So it's refined further, and then here your saturation change and pressure changes are captured with more clarity as compared to in these larger blocks. Local grid refinement should be used with caution due to two main potential adverse consequences. Of course, one is that in capturing flow between the large block and small block, you could have some oscillations in results, but most simulators capture local grid refinement a large degree with minimal errors. The reverse form of local grid refinement is grid coarsening, and then you see this is the regular grid size, and here the grid has been made coarser. So it involves reducing the number of grid blocks in portions of the reservoir where you do not have rapid changes in saturation. And so what this does basically is it makes your simulation runtime faster, you know, and you can use less computational resources to get that done. Grid coarsening is beneficial in reducing computational and storage memory required for capturing fluid flow. Let me just mention the grid orientation effect. And the grid orientation effect exists where fluid flow, when they are oriented both with the grid, principal grid direction and also diagonally. So if you look at this differencing schemes, this is 5-point differencing, this is 9-point differencing. And you see for the 5-point differencing, the middle grid block interacts with 4 grid blocks around it. But the question is, what if there's contribution from these grid blocks? And so you see that though the 9-point differencing scheme would involve would be more computationally rigorous, it's most likely will be more representative of fluid flow, of course, and this depends on the scenario. That's why I said the orientation of Cartesian grids can have a strong effect on the shapes of the displacement front and breakthrough times. Strong grid orientation effects were reported for highly adverse mobility water floods and for pattern steam floods. So this just shows you for these kinds of systems, you will need to ensure, you will need to sensitize for grid orientation effects to see whether this differencing system would work or you just go for the 9-point differencing system. So our discussion so far has been more on spatial discretization, but there's also the thing in time. So your differential equations are solved both with distance and with time. So time discretization results in time steps used to advance the simulation model. So let's say you want to look at your production from 2021 to 2025, you know. So you'll be looking at calculating pressures or saturations within the block and with time. And so the different rows here are referring to different time scales, where along the lines here, you're looking at pressure across the reservoir system. And so this is where the issue of time steps come in. You could do, because the smaller your time steps, the longer it will take for your simulation model to run. And of course, you need to look at, it's also a function of the frequency of the production and pressure data you have, especially your production data. Of course, if your production data is given on a daily basis, your time steps has to be on a daily basis or less. You know. So this can automatically be set within the simulator environment. Of course, you could do that manually, but of course, you need to skilled in that. So if you take reservoir simulation course at a higher level, you will definitely, this will be discussed further. And this relates to how pressures and saturations are calculated within the reservoir simulation environment. So you have 3 main methods. You have the implicit pressure, explicit saturation method. This is your typical just escapes me for a bit, but your refer as impulse method, and then we have the 2 major methods are impulse and the implicit method and the sequential method is somewhere in between. So the thing about the full implicit technique is that all your variables, that's pressure and saturation, are calculated at the new time step. But for the inverse method, that's for the implicit pressure, explicit saturation, what is done is that you solve for pressure at a new time step using saturations at the old time step, and then you now go use the pressure calculator to evaluate saturations at a new level. I wouldn't emphasize further on this. When I was in, I think figure 1 or so, when we're talking about the major steps in reservoir simulation, we saw that you need to initialize the model. So the initial conditions of the reservoir based on input data must be established. And this is like you want to set the model such that it's equivalent to or similar to the state of the reservoir prior to a particular operation, maybe prior to production outrightly or prior to the adoption of a particular process. So basically what you are doing is at that point, you'll be setting your contacts, pressure at the contacts. So input data consists of pressure at a given datum depth of fluid contacts, capillary pressure at the contacts, densities, and if you have different fluid systems, you also might need to specify that during the initialization process. So one thing, basically, at the fluid initialization process, your simulation model, your in-place volumes, your original fluid in place will be calculated, and therefore you can use that to see evaluate the difference between your actual reservoir and because if your volumes are wrong from the initialization process, it would definitely affect. When I mean wrong, I mean if the disparity is large, it also affects your simulation results. So a good rule of thumb is to ensure that division between volumetric calculation and then your simulation model is not less than 2%. So the initialized model is what is now taken in for either history matching or prediction, of course, depending on the data available. So let me speak briefly about history matching. History matching is the process of adjusting the properties and parameters of the reservoir model to match past actual performance measured on the reservoir. So the idea is this: for a field that is already under production, you would have pressure data, or you should have pressure data, you should have production data, and what you're trying to do is to see. So, first of all, you've initialized the model. So initialization ensures that your volumes are similar to what you have in the actual reservoir. But the next thing is to ensure that the dynamic behavior of your model is similar to your field. That if you run your model for 3 years, would it produce the same amount, a similar production, that's oil, gas, water, and then would your pressure values, whether it's at the tubing head or flowing or static pressures, are they similar? And it's typically an iterative process. So the issue matching process is a classical example of an inverse problem, which leads to a non-unique solution or response. This means that different history match models can be achieved by using the same data. The history match models are non-unique solutions applied to performance data, and they can yield different predictions. So you need to have a way of, even though it's a non-unique, it's an inverse problem, you need to find a way of using your engineering knowledge to reduce the uncertainties. So the process of history matching a reservoir model varies from, of course, one engineer to the other, and of course, experience level. And it also depends on the reservoir model type and the quality of data and objectives. For instance, if the reservoir model is constructed from sparse data, and then if you have limited production and pressure data, it's most likely that your history matching process will also be limited. So this goes to show that with acquisition of more data, much more production, more pressure surveys taken, the confidence in your model begins to increase. And of course, you have a better output from the history matching process. So generally, the history matching process can be divided into two phases. There's the pressure match phase and the saturation match phase. Okay, this is the traditional way to do it. There are different approaches, but this is the traditional way to do it. So the pressure match phase normally precedes the saturation phase. So during the pressure match phase, the history matching process is focused on matching net voidage from the reservoir with the aim of matching pressure distribution over a specified period of time. So the idea is for bulk volumes withdrawn from your reservoir system, do the pressures, either flowing or static pressures, depending on the data you have, do they produced by your model, do they match what you have in the on the field? In some cases, only a match of the trend of the pressure distribution can be achieved. The goal during the pressure match phase is to obtain a reservoir model that approximates the net volume of fluids in place during the duration of the history. During the pressure match phase, minimal effort is applied in validating the distribution of phases of saturation. So basically, we are looking at, for the underground withdrawal or the voidage, does my pressures match what I have? And you want to get a pressure match that is similar to what you have on the field. At the end of the pressure match phase, then we go into the saturation match phase. And attention is directed towards specifying your distribution of phases around the wells and different zones of the reservoirs. For instance, in history matching a black oil reservoir model, all production rates are typically specified, and then of course water, gas, or either your gas oil ratio, and BSMW would also be specified. Also, pressures and other performance data are compared. Different forms of actual data are compared, but I think the core thing is to look at your oil production, look at your gas oil ratio, look at your water oil ratios, of course, from different wells, and then you look at your average reservoir pressures. So matching of the data predicted by the model to that of the actual well can be performed at field level or group of wells or individual well. Of course, you know that matching saturations and pressures on a well basis is more hectic than looking at it at a reservoir model. So you could actually look at this as, first of all, you look at a reservoir-wide or field-wide match, and then you now begin to look at the match from the different wells. So there are times when you have a good match from the field data or on a reservoir basis, but when you go into the well basis, you now begin to see disparity. And I think one thing I've not addressed here is what data are you going to tune? Because you have your production data, you have your pressure data. So what data would you tune in your model to ensure that you have a good match? And this is where, so in number of discipline teams or asset teams, they'll come up with a risk register, or they'll identify parameters for which there's a large uncertainty. For instance, let's say your permeability values are based on build-up pressure surveys, and you can have an average, maybe have an average permeability value of 1 DASI. But that's an average value. You don't have, and let's assume you don't have core data. That means you have large uncertainty around your permeability distribution in the field. It could also be porosity. So values, parameters for which you have very small uncertainty, you are not used as major tuning parameters. Some of your major tuning parameters will now go into your relative permeability. So you come up with that register, identify the parameters, look at the uncertainty range, and that tells you parameters that can be tuned in order for you to get a suitable match. So generally, history matching process is terminated at the point where the team engaged in the effort, decides that an acceptable match has been obtained. And of course, that tells you that you must have some metrics to determine that. The following best practices are recommended to enhance the efficiency uh, and effectiveness of a history matching process. So one, make a log of all activities and changes made on the model during the history matching process. This log should be maintained preferably within the model. When the history matching is conducted by a team, all members should ensure that all changes made to the model are documented and nothing left out. The changes made on the model during the history match process should be graduated and systematic. Haphazard changes to the model should be avoided, and the clear and defined results expected from the history matching process should also be stated ahead of time. The results from previous changes or adjustments to the model should be analyzed and understood before you go ahead with the history matching process. So it's advantageous for the teams, members of the teams, to agree on the parameters which will be tuned. So the least reliable data should be modified first. For instance, if permeability data are least reliable data, then of course permeability data would be tuned during the matching process. Further changes to permeability data beyond your uncertainty band will lead to unreasonable results. So you see, in history matching, you could get a match could be obtained by tuning any of the parameters, but is it realistic? Is it within the your uncertainty band? Are the values of the parameters which you are settling for, are they realistic? So recognition of the point in the history matching process when further changes in the input cause insignificant and improvement is important. This is the point of diminishing returns. And so you must have a cutoff point where you have an objective function, you have an error function, and you determine when your error function is not being minimized further, and therefore you put a halt to the history matching process. Of course, history matching can be done both manually and automatically. Like when we treated T Navigator, there was an assisted history matching module, and of course, what the automatic history matching process helps you to do is so that the tuning of the parameters can be done in a systematic manner. The use of automatic history matching can remove specific knowledge and experience, and of course, it will help the teams look at the history matching process objectively and with bias minimized. The objective function is defined as the function of the difference between the observed and the simulated behavior, So you are usually minimizing that. And of course, once you have a model which you've matched and you've tuned it appropriately and the team is satisfied, the next thing will be to go ahead to predict future performance, So it is wise before you go ahead to evaluate, probably you want to look at um, the value of deploying a miscible gas flooding strategy. You will have done your history matching so that you will have good confidence in your prediction process. For new reservoirs with little or no production history, initial well production rates may be adjusted using productivity index from drill stem test or extended well test. For this, for new reservoirs, it's impractical to carry out any form of history matching. Basically, what you are just doing is to ensure that your model is well initialized, and of course, probably your productivity indexes and all are realistic. So history matching has value for mature brown reservoirs or mature systems where you have some good and reliable pressure and production data. So in conclusion, I would just like to say that even though I mentioned uncertainty later, so we tend to there's no one realization which is completely accurate. So you need to generate multiple realizations, capturing uncertainty in the data, there's always uncertainty. It's just that the level of uncertainty decreases with more data acquired. And traditionally, we do the P10, P50, P90 quartile models. But now, for now, we can actually, we're not limited to those levels of uncertainty. More realizations can be generated. And one of the processes used to evaluate the impact of uncertainty is referred to as the experimental design, design of experiments. And these algorithms are incorporated into post simulators for many of the commercial simulators. So you could always evaluate that. This view graph, so you look at this. If you look at this view graph, you see these are multiple realizations. Of course, you would have a base case, and then you look at the multiple realizations and see how that impacts on your production forecast. And then with this, you can have a good degree of confidence in your work. That'll be all for now.